This is a review for Unit 8, Exponents. Our first rule is the product rule. This rule says that when you're multiplying two different terms that have the same base, you can add together the exponents. Conceptually, what we're looking at here is, like this 4 has an exponent of 1. And this is 4 times 4, and this is 4. How many 4s total do we have? 3 of them. You can write that as 4 to the third. The shortcut is to just add the exponents. You could also count how many 4s. Both work. If you go to your calculator and you press 4, the caret key, and then 3, you'll get 64. With this one, we have to think about how many negative 2's there are. On the left, there's 2 of them. On the right, there's 5 of them. Altogether, there are 7 negative 2's. I can also think of this as 2 plus 5. If I resolve this in my calculator, I'm going to get negative 128. Keep in mind this negative is not inside the parentheses. So negative x to the 6th would be a different situation. That's not what this is. Negative is not part of the base. So this is like negative 1 times x to the 6th times x to the 5th. And we leave the negative and we add together the exponent, 6 plus 5, negative x to the 11th. When there's letters, you can't solve it in the calculator. You just simplify and then you're done. Here we can multiply numbers. 9 times 7 is 63. And we can multiply q's. This is q to the 2 plus 1, or 63q to the third power. Now notice 9 and 7 don't have the same base, so it's not like we're adding exponents, we just multiply. A similar thing occurs here. Negative 5 times negative 7 is a positive 35. K to the third. 2 plus 1. How many k's? 2 from the left, 1 from the right, a total of 3. This one is different because we have different letters. Just like before, we want to look for the same bases. So the x's, there are 10 of them. The y's, there's only 2. And the z, there is 1. So we can combine to the third power and to the 7th power to get to the 10th power. So for the product rule, we are adding exponents when you multiply with the same base. If you ever are just multiplying numbers times numbers, that's okay too, but it has nothing to do with exponents. A very key difference is when negative 2 is inside the parentheses versus something not being in parentheses. It happens differently. This is like negative times x times x times x 6 times, where this is like negative 2 5 times. The parentheses matter a lot for negatives. Next up is the quotient rule. Here we're going to be subtracting when we are dividing two exponents with the same base. So think about what exponents mean. That's 6 times itself 6 times, 6 times itself 4 times, and we cancel out 1, 2, 3, 4 of them. On the top is 36. We can also think of this as 6 to the 6 minus 4 is equal to 6 squared, which is 36. Here we have 4 to the 8th divided by 4 to the 5th. We cancel out 1, 2, 3, 4, 5 of them. There's 3 left on top. That's going to give us 64. The shortcut is to just subtract. 8 minus 5. Remember here that x has a 1. So if you think about how many x's are on top and the bottom, you cancel out 1. There's 4 left on top, x to the 4th. You can also use subtraction. 5 minus 1 is equal to 4. So if you think about this as x times x times x over x times x times x, they all cancel out. And what are you left with? Just 1. You can also think of this as x to the 3 minus 3, which is x to the 0, which by default will always be 1. Here we can subtract x to the 9 minus 1 and y to the 2 minus 1. This gives us x to the 8th and y. We could put a 1 there, but that's for the rookies. It can be confusing when you're subtracting and there's different letters and some are on the top and some are on the bottom. So you can also think of it like this: QRST on top, QQXY on bottom. I expanded the q squared. What happens? One set of q's goes away, and I'm left with RST still on top, and QXY still on the bottom. That's it. Nothing else I can do because there's no repeats of any of the other letters. The only one that showed up on the top and the bottom was Q, so I could simplify it a little bit. When it comes to the quotient rule, we look for the same base on the top and the bottom of the fraction, and we subtract the exponents. If a letter is only on the top or only on the bottom, we do absolutely nothing with it. If there's not a number, we assume that the exponent is 1. Next up is the power rule. We have a base raised to a power raised to another power. In this case, what we do is we multiply. And this gives us 2 to the 12th, n to the 18th, or a to the 8th. Whether it was positive or negative, sometimes you have to multiply two negatives. For example, you could end up with something like x to the negative 2 raised to the power of negative 2, and that would give you x to the 4th, because when you multiply a negative times a negative, it turns out positive. And that's all you have to do. Here's an extension of the power rule. What do we do with that power rule when there's more than one term inside of the parentheses? Now technically we could use the order of operations and figure out that this is 8 to the 3rd power, which is 512, but we can't really do that in the next one, because 5 and x are not like terms. So instead, it's almost like we distribute the 5. And the 5 has an exponent of 5, and the x has an exponent of 5. 5 can turn into 3,125, but there's no answer for the x, we just leave it as it is. You can think of this two ways. You can think of whatever's inside of the parentheses times itself 9 times, or you can distribute the exponent, and this becomes x to the 9th, y to the 9th. Because how many x's are there in total? There are 9 of them. So we can write that as x to the 9th. Same thing with y. As long as you're multiplying everything like this, the order doesn't really matter, and we can rearrange things into these exponents. Here, keep in mind that negative 10 is a separate term from m. So I can take negative 10 to the 3rd power, and I can take m to the 5th to the 3rd power. And now we're back to the power rule, and we're doing it separately for each term. I'm going to put a 1 there because there's no exponent here. So this is negative 10 to the 3rd. That's going to give me negative 1,000. And m to the 15th, 5 times 3. I'm going to put a 1 there to represent the invisible exponent 1. And when I distribute, I get x to the 2 times 3 and y to the 1 times 3. Or x to the 6th, y to the 3rd. And I'm done. There are 2 levels of parentheses in this one. So I'll start with the inside one. This becomes q squared r squared, st. And then I distribute the 4 to each term. Each letter is considered a different term. This becomes q to the 8th, that's 2 times 4. R to the 8th, 2 times 4. S to the 4th, and T to the 4th. When it comes to power of a product, you can think of the inside the parentheses term as being multiplied by itself, or you can think about distributing the exponent. I think it's a little bit faster and doesn't require as much writing, but both will absolutely work. It's important to remember that when you have a negative, you include that inside parentheses when you use your calculator. Otherwise, you might get the wrong answer. This next rule is very similar. It's using the power rule and the quotient rule together. And just like before, we're going to be distributing our exponent into each term. Here, this becomes 4 squared divided by 17 squared. I can simplify this to 16 over 289. Notice if you left this as a decimal, it would not be correct. Here we are simplifying, so we want to leave everything as fractions. Let's think of this 2 ways. We can rewrite this as negative 1/3 times itself 5 times. And if you know anything about fractions, you just multiply straight across the top. Since there's an odd number, that'll give us negative 1. And straight across the top, that's 3 times 3, 5 times. And we get 243. If that method works for you, great. I think it's simple to just distribute the 5 and resolve them separately. If you enter this in correctly, you'll be able to get an answer in one shot on the calculator. Make sure you're using parentheses. We distribute the 4, and it's like x to the 4th on top, y to the 4th on bottom, and that's all we can do. There's nothing else to simplify, and there's no actual solution. There's a lot of things to distribute the 3 here. 2 terms on the top and 3 terms on the bottom. Remember, on the top we're going to use power rule, so 2 times 3 is 6. None of the other terms have an exponent other than 1, so we don't have to worry about that. Elsewhere they all just become 3. Now we can use the quotient rule. If we look at the x terms, this is like saying x to the 6 minus 3, and y to the 3 minus 3, and z to the 0 minus 3, because there's nothing on top. If that doesn't make a lot of sense to you, you can always go back to this sort of diagram and cancel out 1, 2, 3 of the x's, 1, 2, 3 of the y's, and write what's left. There's 3 x's on top and 3 z's on bottom. This will give you the same result though. 6 minus 3 is x to the 3rd. Y to the 3 minus 3 is y to the 0, which is just 1. And z to the negative 3 goes to the bottom as a positive 3. I distribute the 3 to the top and the bottom. This becomes x to the 3rd divided by y to the 6th. And I'm done. For power of a quotient rule, we are distributing the power to each term on the top and bottom separately. Sometimes we have to multiply if there's existing powers already there. You can think of it as the quotient rule where you subtract, or you can think of it as dealing with each term separately. Both will work. If you struggle with subtracting, write them all out and cross out which ones cancel out. The 0 rule says that anything raised to the power is always 1. So 500 to the 0 power is 1, x to the 0 power is 1, 5z to the 0 power is 1. This one's a little bit different because there's no parentheses, so y is raised to the power of 0 and then multiplied by 12. So this becomes 12 times 1, or just 12. So pay close attention. That doesn't happen here because 5z is inside the parentheses. For the negative exponent rule, instead of multiplying by 3 over and over and over, we're multiplying by the reciprocal of 3 over and over and over. So think of it as 1/3 times 1/3 instead of 3 times 3. And that'll tell you the answer, 1 over 9. Alternately, whenever you see a negative exponent, you just flip it and make it positive. And that will also give you 1 over 9. That strategy works a lot better when we have variables. If there's a negative exponent, put it to the bottom and make it positive. 1 over x to the 3rd. Remember that if you have 2 different terms here, x and y, without parentheses, the y is the only one raised to the power of negative 4, and then it's multiplied by x. So if I was to rewrite this, y to the 4th goes in the bottom, but x stays on top. A similar thing happens here. K is raised to the negative 3 and multiplied by 5. So 5 stays on the top, k to the 3rd goes to the bottom. What happens if we have a negative exponent starting on the bottom? Well, we still flip it, and now it goes to the top. And we don't usually write over 1, we just leave it as x to the 3rd. Here we plug in a value for t. So we plug in a 2 to the negative 6, which is the same thing as 1 over 2 to the 6th. If we put this into our calculator, we might get 0.015625. Don't forget to press Math, Enter, Enter, because we want to leave all of our answers as a fraction, which is 1 over 64. Here we see the power rule with a negative, so this is 5 to the 3 times negative 3. Which makes it 5 to the negative 9th, which makes it 1 over 5 to the 9th, which means we're looking at 1 over 1953125. Similar thing here occurs, negative 2 times negative 1. And this is the same thing as 2 to the 2nd, because the negatives cancel each other out. And 2 squared is just 4. The old switcheroo. 6 goes to the top, 2 goes to the bottom, now they're positive, and you're done. Remember for negative exponents that If the negative exponent starts on top, it goes to the bottom. Be aware that without parentheses, a negative exponent only goes to the nearest term, so leave the x's and the 5's on top. If your negative exponent starts out at the bottom, flip it to the top. When we're taking power to a power, negatives can cancel each other out. Remember, with letters, we can't actually find an answer, so just simplify as best we can. Move things around to the top or the bottom, and stop there. Our last exponent rule is about fractional exponents, or rational exponents they're sometimes called. And the trick here is that the number on top is the power, and the number on the bottom is the root. What do I mean by that? Well, m raised to the 1/7 is the same thing as the 7th root of m to the first power. That's it. And z to the 1/4 is the 4th root of z to the first. We are just rewriting these. So what does this mean? Can we go to our calculator and plug this in directly like this? We could. We can also think of it as the 4th root of 256 to the first power. Both of these will work. The answer for either one of these is going to give you 4. When we say to the power of 1/3, that's like the cube root of 64. So what number times itself 3 times is going to give you 64? That answer is 4. With this one, we have the cube root of negative 64 squared, and remember it's 1 over all of this because we have a negative exponent. So for this one, you have to put it in the calculator correctly. You can either directly use this first part, or you can do it one step at a time and take negative 64 squared, get an answer, which is 4096, and take the cube root of 4096, which is 16. So our final answer there would be 1 over 16. If you know how to use the calculator correctly, because there's no letters here, you can plug it in directly like this, and you'll get the same answer. What does it mean when I have a root and a power? Well, first, this part right here, the root, is distributed to each term underneath the bracket. And what it does is instead of multiplying the powers for each, it divides. So the 3 goes to each of the terms inside the radical. And this whole thing is raised to the 9th. So now I have 3 to the 9/3, x to the 9/3, and z to the 9/3. Well, that's just 3 to the 3rd, x to the 3rd, z to the 3rd. And I can simplify 3 to the 3rd to 27. And the other ones keep their exponents and go from there. The next one is power to a power. So this is x to the 2/3 times 3/2. Well, you might notice that if you multiply across the top, you get 6, and across the bottom, you also get 6. So this is x to the 1. So a is equal to 1. Simplifying this one, this is the 3rd root of a squared. Nothing you can do with the calculator in terms of a trick for this one because it has letters. You just have to remember that the bottom one is the root, the top one is the power, and rewrite it. This one has a root of 2. When there's not a number, it's assumed to be 2. That's where square root comes in. Square is the 2. So what do we do here? We distribute it to each term, and this becomes 9 to the 1/2 and x to the 2 over 2 because you're dividing them both by 2. You can also think of that as the square root of 9 and the square root of x squared if you want to. Either way, you'll end up with 3x as your final answer. So fractional exponents is just a different way of looking at roots. 1 over 7 is the 7th root of something. 1 over 4 is the 4th root of something. That's really what the fractions are for. But if we have a number that's not 1 on top, that's where we include a power as well. So the 3rd root of something that is squared. Like before, power to a power involves multiplying. But new on this one is we had a number outside of a root that we distributed to each term inside. We saw that with powers before, but here we're distributing roots. And you have to divide by that 2 or that 3. When there's no number, it's a 2. On to the fun one, the combined properties. So one way to think about this is 4 times 3x on top and 2x times 2x on bottom. What that allows us to do is to multiply all of the numbers first. 4 times 3 times 3. That gives us 36. and add up how many x's there are. There's 2 of them. On the bottom, I can take 2 times 2, which is 4, and add up how many x's. Since there's 2 x's on the top and 2 x's on the bottom, they cancel out. And what is 36 divided by 4? The answer is 9. A lot of what we're doing here is simplifying and crossing things out to find a shorter answer. We distribute the 5. This is like 3 to the 5th, z to the 5th, z to the negative 8. We can add together, so we have 3 to the 5th, and then we have z to the 5 plus a negative 8. So this is like 3 to the 5th, z to the negative 3. 3 to the 5th is 243. To make this exponent positive, we move it to the bottom, and there's our answer. So for this one, remember that there's different terms. We have negative 5 raised to the negative 2. We have n to the negative 6 raised to the negative 2. And I'm going to think of the negative 1 in front of this as a whole separate term. To the negative 2, n to the negative 6 to the negative 2, and m to the 9th raised to the negative 2. A lot of distributing here. This one is effectively going to be like 1 over 25. Negative 6 times a negative 2 is a positive 12. And I'll put over 1 just to keep things organized. Negative 1 on the bottom is going to be like 1 over 1. This one is going to be negative 6 times a negative 2, which is n to the 12th. And 9 times a negative 2 is negative 18. So this one I'm going to move to the bottom as a positive 18. And I combine. How many n's are there? 24. 25 m to the 18th on bottom. The key here was recognizing that you had to distribute 5 total times. The negative is not associated with the n inside of parentheses. Here we distribute the 4 a couple of different times. We have 3 to the 4th, n to the 12th, that's 3 times 4, m to the negative 28, that's negative 7 times 4. 3 to the 4th, I can get an answer, that's 81, n to the 12th, m to the 28th. Because to get rid of the negative, I move it to the top. So 6 over 3 is one thing, and then x to the 5th over x to the 3rd is another. I can simplify that to x to the 5 minus 3. So 2x squared is my answer. This is like 3 to the negative 2 over 7 to the negative 2, and I can flip it and write 7 squared over 3 squared. And this is 49 over 9. To cancel out the negatives, I'm going to put the 5 on top and the 4 on bottom, and I'm actually done. If there's 5 x's on top and 3 on bottom, I'm going to subtract to find the difference. If there's 7 y's on top and 9 on bottom, I'm going to subtract to find the difference. I get x squared, y to the negative 2, which is the same thing as x squared divided by y squared, because to remove the negative exponent, I flip it and make it positive. I'm going to distribute the 2 to everything. So I have 4 squared p to the 6th, 2 squared p squared q to the 8th. Notice it was different when there was an exponent. I had to multiply, but otherwise I'm just distributing. So I can answer what 4 squared and 2 squared are. And notice the p's. There's 6 on top and 2 on the bottom. So if I cancel out 2 of them, how many are left? 4 of them. And what is 16 divided by 4? That's just 4. And I'm going to leave the q over 8 on the bottom. Remember, I distribute the root to each term inside the parentheses. This is x to the 3 over 3, y to the 6 over 3, x to the 1, y squared, or just xy squared. It's assumed the root is 2. For square roots, that's the default. This becomes x to the 8 over 2, y to the 4 over 2. I can rewrite those as x to the 4th, y to the 2nd, and I'm done. I distribute the 3 to the c and to the d, which I multiply there. I distribute the 2 to the c and the 2 to the d. And now, since I'm multiplying them, I add them together. C to the 13th, that's 3 plus 10, and d to the 22nd, that's 18 plus 4. If I plug in values here, 8 to the power of 0, and 10 to the power of negative 2. So 8 to the 0 is just 1. And if I want to get rid of the negative exponent, I can make this 1 over 10 squared, which is just 1 over 100. Make sure you write it as a fraction and not as a decimal. To simplify this, I multiply power to a power. So this is 1/3 times 3. And that just goes away. And I'm left with x. For the y, I have y to the 5 divided by 5, and that goes away, and I'm just left with y. If I distribute here, I have a to the negative 3 times 3, b to the 4 times 3, a to the 2 times 5. That's a to the negative 9th, b to the 12th, a to the 10th. I can add together my a's because they're the same base, and I have just one of them because I subtracted 9, and the b to the 12th stays the same.